Welcome back. These are the section 5.2 notes, power functions. This is page 4. So let's talk about multiplicity. We just looked at that a minute ago. I thought I took enough time to stop coughing. Whatever. The multiplicity is how many times a factor happens. Okay, so just so this is in the notes and the answer key. Okay. If the multiplicity is odd, your curve or the graph will cross the x-axis. Okay. The higher the power, the more it kind of flattens out as it crosses. If the multiplicity is even, the graph will touch the x-axis and bounce off. So it touches and goes back to whence it came. Again, in both cases, let's slide that up a little. The higher the power, the flatter the graph is at that x-intercept, or 0. Because keep in mind, even if it doesn't cross, it still does hit the x-axis. So you do still have an x-intercept there. So let's go ahead and find the zeros here and talk about multiplicity. I have 4 terms. So I'm going to start by factoring by grouping. I'm going to group my first 2 terms. And I'm going to group my second 2 terms, but I want to make sure that negative stays with the 9x, so I'm going to put a plus in between them. I can factor x squared out of the first 2 terms. And because I want what's left over to match inside here, I am going to factor out a negative 9. I got an x minus 2, x squared minus 9, which factors completely into x minus 2, x minus 3, x plus 3. My zeros are x equal 2, multiplicity 1, powers 1, x equals 3, also multiplicity 1, so this is not very exciting, and x equals negative 3. With multiplicity 1. We can go back up to this last example where my x equals 1 has multiplicity 3, and my x equals negative 2 has multiplicity 1. Okay. So not super exciting with multiple multiplicities, but a quick review of factoring by grouping and the realization that even though when we factor we don't always state it, if it happens once, it has multiplicity 1. Okay. Our number of zeros. Every polynomial function with degree n greater than 1 has n zeros. They may be real, rational, they may be irrational if we are using the quadratic formula to find them. They could be complex, non-real. If one root has multiplicity 2, that's going to count as 2 zeros. Okay. To the following example. And I did graph this and drop this into the notes. I graphed this using Desmos. A couple of things when you use Desmos. Desmos does not like any variable other than x. So our input variable has to be changed to x. Okay. I also used the table function to find the y values for the required x's. To do that, so to be able to use the table function, I need to let Desmos know that's what I'm going to do. So I plugged it in like this. The subscripts in Desmos, you're just going to type in y and then 1 for y sub 1. And x and then 1, no space, for x sub 1. Then I can use the table function. Change the subscripts at the top of the table to x sub 1 and y sub 1. It's going to automatically give you x sub 2 and y sub 2 since you used the subscript 1 in your equation. And then all I need to do is type in the x's that I want, and it's going to give me the y. Okay. We are using this quartic, fourth degree polynomial function to estimate the number of milligrams of pain relief medicine, ibuprofen, in the bloodstream T hours after you take 400 milligrams of the medication. We want to figure out what that is at time 0, 0.5, 1, 1.5, and so on. So you'll notice it peaks and then drops. If you were doing this by hand, if I was figuring this out, it would be 0.5 times 0 to the 4th plus 3.45 times 0 to the third minus 96.65, 0 to the second, plus 347.7 times 0. Everything's multiplied by 0. It's obvious this one's 0. Notice that after 6 hours, the dosage is, or the amount of ibuprofen in your system is back to 0. So most of the time these say between 4 and 6 hours. And between 4 and 6, as this part of the graph is decreasing radically, we got this part increasing. So that at 2 hours, when it's completely out of your system at 6, that next dose is at maximum strength.